So, you have a massive large language model and you want to serve it to thousands of users. But here is the problem. These models are memory-hungry giants. If you try to run them on a single server, you will hit a wall fast. Today, we are going to master Ray, the secret weapon for distributed LLM deployment. We are moving from single machine scripts to production-grade clusters. Ready? Let's dive in. Why Ray? Well, think of Ray as the conductor of an orchestra. In the world of AI, your GPUs are the musicians. Ray manages the complex task of scheduling, memory sharing, and failure recovery across a cluster of machines. It uses an actor model, which means every model instance is a self-contained worker that can live anywhere in your cluster. This is how we achieve true horizontal scaling. Before we write code, we have to talk about the memory wall. An LLM like Llama 370B requires about 140 gigabytes of VRAM just to load the weights in 16-bit precision. Most GPUs only have 24 to 80 gigabytes. This is why distributed computing isn't just a luxury. It's a hard requirement. We have to split the model across multiple GPUs using techniques like tensor parallelism. Now let's talk about the KV cache. This is where most engineers get confused. When an LLM generates text, it looks at every previous word to predict the next one, instead of recalculating everything. We store previous keys and values in memory. But here is the catch. As the conversation gets longer, the KV cache grows, and it grows fast. It can actually consume more memory than the model itself. This is where vLLM comes into play. In a standard setup, memory for the KV cache is allocated in big, contiguous chunks. This leads to massive waste. We call it fragmentation. vLLM solves this with paged attention. It treats GPU memory like a computer's RAM, breaking the KV cache into small pages that can be stored anywhere. This allows for much higher batch sizes and throughput. To fit these models on cheaper hardware, we use quantization. Think of it like compressing a high-resolution photo. A 16-bit float uses a lot of space. By converting those weights to 4-bit integers, we reduce the memory footprint by 4 times. Yes, there is a small hit to accuracy, but for most applications, it is barely noticeable. This is how we run huge models on consumer-grade GPUs. Warning: not all quantization is equal. Techniques like AWQ and GPTQ are smarter than basic rounding. They identify the most important weights, the salient ones, and keep them at higher precision while compressing the rest. When you are deploying on Ray, choosing the right quantization method can be the difference between a fast response and a total system crash. When one GPU isn't enough, we use model parallelism. In tensor parallelism, we split individual matrix multiplications across GPUs. In pipeline parallelism, we put different layers of the model on different GPUs. Ray makes this easy by managing the high-speed communication, usually over NVLink, so the GPUs can talk to each other almost instantly. Now let's talk about Ray Serve. This is the production layer. It provides an HTTP interface for your models, but it is not just a simple web server. Ray Serve handles load balancing. It knows which worker is busy and which is free. It can even route requests based on the model version, allowing you to run A/B tests or canary deployments with zero downtime. Scaling isn't just about adding more GPUs. It is about doing it dynamically. Ray's autoscaler monitors your request queue. If the latency starts to climb, it automatically spins up new worker nodes in the cloud. When the traffic dies down at night, it shuts them off to save you money. This elasticity is why engineers choose Ray over static Kubernetes deployments. Don't ignore small language models, or SLMs. Models like Phi 3 or Mistral 7B are incredibly powerful for their size. On Ray, you can pack dozens of these smaller models onto a single GPU node. This is perfect for specialized tasks like summarization or code completion. Sometimes, a fleet of small, fast models is better than one giant, slow one. How do we measure success? You need to track two key metrics. First, time to first token, or TTFT. This is how fast the user sees the start of the response. Second, tokens per second, which is the overall generation speed. A high TTFT usually means your KV cache is struggling to load. Ray's dashboard gives you these metrics in real time. Let's talk about continuous batching. In the old days, we waited for a whole batch of requests to finish before starting a new one. That's a waste of time because some sequences are shorter than others. Continuous batching allows new requests to join the batch as soon as one finishes. This can increase your throughput by 2 to 3 times without any extra hardware. The biggest mistake I see: out of memory, or OOM, errors during peak traffic. This usually happens because the KV cache wasn't limited correctly. Always set a max model len in vLLM and monitor your Ray dashboard for memory spikes. If you see fragmentation rising, it is time to adjust your page sizes. Don't wait for your users to tell you the system is down. We have covered a lot, from Ray actors to paged attention and quantization. You now have the blueprint for expert-level LLM deployment. Remember, start with a small model, optimize your KV cache, and use Ray to scale only when you need to. The world of distributed AI is complex, but with these tools you are ready to build something amazing. Keep building.